classes are going to be conducted. So for today, my plan would be I will start off with radar plotting. I will start off with a basic radar plot today. And if we cover up that basic radar plot in time, then after that I'll stop, take a pause so that you can practice this basic radar plot today. And then in the next class, I will go for advanced problems on radar plotting, predicting action to take, okay, as per ROR, what are the actions are required, restricted visibility, target taking action, own ship taking action. So these are advanced concepts. So this I will do in the next class. So today we will pick up a basic radar plot, and along with it, I will pick up a simple theory topic so that you don't get overwhelmed and overloaded with homework on the first class itself. So that's the plan for today. So this was the introduction beta. Now, any doubts coming in your mind, please share with me. All good?
Yes, sir.
Okay, beta. Great. Okay. So one thing which I want to ask you is just to sense the pulse of the group. You want me to go right from the basics, or shall I take it for granted that the basics are already known to you and we can go slightly on a top notch? What do you want me to do? Are you familiar with the basics already? You want to go directly to the higher level, or you want me to start right from bare basic, considering that you don't know anything?
So start from basics.
No.
Okay, beta. All right. Okay. I got a feedback earlier also from some candidates. They wanted me to start right from the basics. So that's what we will follow. Okay, great, beta. So if you are comfortable, shall we move ahead with our presentation?
Yes, sir, we can.
Yes.
Okay, great. So first of all, I will show you the examination format. And once you are familiar with the exam format, then we will move on to radar plotting. So let me put up the exam format to you. Just give me 1 minute. Okay, beta. All right. So I hope all of you can see the examination format now on your screen.
Yes, sir, we can.
Okay, great. Sometimes when I show something, there may be a slight time lag on your side. That is because of the internet speed and all. So if you are not able to see it immediately, just wait for a couple of seconds. In some time, 3, 4, 5 seconds, it should be visible. Okay. So as you see in the exam format beta, this navigational aids and compasses is a 3 hours paper, and the total marks are 200 marks, out of which the passing marks are 100, so 50% passing. Now, in this paper, the first 3 questions are compulsory. What are these compulsory questions? The first question is on radar plotting, not more than 3 targets. The second question is on gyro compass. This could be a theory or a numerical kind of question. And the third compulsory question is on magnetic compass. In magnetic compass, we have only theory in our syllabus. However, there are small, very basic numerical questions also which come in our exams. So when we go to the magnetic compass, I will explain you about those questions also. So these are the 3 mandatory questions. Now, after these, you have another 6 questions, 4, 5, 6, 7, 8, 9. Out of these 6, you have choice of 1. So you need to do any 5 questions out of these 6. These questions are on autopilot, course recorder, rate of turn indicator, logs and echo sounder, then performance standards of the navigational equipment, only for GPS, AIS, VDR, SVDR, echo sounder, rate of turn indicator, SDME, speed and distance indicator, that is the log, and BANVAS. Then we have electronic position fixing system, that is the GPS. Then we have number 8, AIS and LRIT, long range identification and tracking. And number 9 is on voyage data recorder or BANVAS, bridge navigational watch alarm system. So these are the topics on which we get the questions in our paper. So we will be following this sequence. I'm starting off with radar plotting and touching upon the echo sounder for today's class. So any doubts in the examination format, beta?
No, sir.
Very good, very good, beta. Great. So let's now move on to our first topic of radar plotting. So I'm starting from bare basics. For radar plotting, you need to have that shipborne radar, Captain Subramaniam's Nutshell series book. So let's go into the radar plotting. I will tell you how a basic plot is done. So let's go. So I hope, beta, you can see the opening slide on radar plotting now. Everybody is able to see. Anybody having any doubts or issues?
No, sir, it's good.
Very good, beta. Great. Now it is possible, beta, sometimes some of us may get disconnected because of disruptions. So in case I get disconnected, just wait for some time. For a couple of minutes, I should be able to reconnect. So if any issues I am facing and I am not able to reconnect, I will pass on the information to you on the WhatsApp group. So let's start off. As I told you, I will first go through the complete slide. And after I have explained all the points, I will take a pause and ask for your doubts. So if any doubts are there, let me finish and then you can ask your doubts. So with this, let's get into radar plotting. In this presentation, we are going to learn radar plotting. So first we go into the basics. Radar plotting is basically the technique of obtaining the navigational data of a target by observing it on the radar screen. It involves the construction of an OAW triangle on the radar plotting sheet. Plotting is generally done using one of the two methods, a relative plot and the true plot. Most of the time, the plotting which is done is the relative plotting or the relative plot. True plot is rarely used in actual practical situations on board. Now for doing the radar plotting, the material which is required is number 1, the radar plotting sheet, then the plotting tools like pencil, eraser, compass, ruler, protractor to draw angles, and a tool to draw parallel lines like a sliding ruler or a set square or a parallel ruler. Clear up to here, beta? Shall we move ahead?
Yes, sir.
Okay. Let us first go into the references which are used to make the plot. Let us open up a plotting sheet. You can see a plotting sheet on the screen now. Now on this plotting sheet, the letter C, Charlie, is used to denote the center of the sheet. So you can see Charlie point coming up at the center of the radar plotting sheet. The alphabet O, Oscar, is used to denote the relative position of the target at the beginning of the plotting interval. Now, whenever we do radar plotting, we need to have minimum 2 observations of a target. The time interval between the 2 observations of a radar plot is called the plotting interval. Most often, a period of 6 minutes or 12 minutes is used as the plotting interval. Now, Oscar point is used to denote the position of the target at the beginning of the plotting interval. So let us take an example. We have taken an observation, observed a target. We have the range and bearing of the target. These are the two data which is provided, to information which is provided by the radar, the range and the bearing of the target. And now we want to plot it on our radar plotting screen. Now for plotting, we need to have a scale. Like you can see, we have mentioned a scale for our particular plot as 1 centimeter equal to 1 nautical mile. So this is the distance scale which we will be using to plot the targets. The bearing can be easily plotted using the graduations on the radar plotting sheet. You can see the graduations. Right at the top you have 0, 0, 0 bearing. Then moving clockwise 0, 1, 0, 0, 2, 0, 0, 3, 0 and so on. So you see these graduations going up to 180 at the bottom, 270 at the left side of the radar plotting sheet, and coming back to 360. So any bearing of the target from 000 to 360 can be easily plotted using these graduations. So let's plot our first observation. Let's assume that the target was here when we started our plotting. So at the beginning of the plotting interval, the target was observed to be here. This was the bearing of the target, that is 020. And let's assume that this observation was taken at 0800. This time is denoted along with the initial position of the target, and it is named as O, Oscar. Charlie to Oscar denotes the range of the target at 0800 observation. This range is measured as per the scale which is chosen, 1 centimeter equal to 1 nautical mile. Now the scale which is used to plot the positions on the plotting sheet should be as large as possible, and this ensures greater accuracy of the plot. Even if a position falls slightly outside the printed circle, it may be used as such as long as it falls on the plotting sheet. Now moving further, alphabet A is used to denote the relative position of the target at the end of the plotting interval. So let's assume that this target was observed to be at this particular position at 0812. So you see we have a 12 minutes plotting interval. The second observation is taken at 0812, and this is denoted by alphabet A, alpha. Now CA, Charlie Alpha distance, represents the range of the target at 0812 hours, And if you extend this CA line to the outer scale, this represents the bearing of the target at 0812. Now, if we join Oscar with alpha and extend this line further, this line Oscar alpha represents or denotes the relative movement of the target. And when this line is produced, this is called or known as the relative line of approach. Let us show the line Oscar alpha on our plot. You can see the Oscar alpha line coming up. It is denoted by two arrows representing the relative line of approach. Now, on this relative line of approach, that is Oscar alpha extended, we can easily find out the closest point of approach with the target. The closest point of approach is also known as CPA. Now, to find the CPA, we drop a perpendicular on the relative line of approach, that is Oscar alpha extended, from the center of the plot, that is point C. So from point C, I drop a perpendicular to the relative line of approach, and the point where the perpendicular meets the line of approach is the closest point of approach, the CPA. It is represented by the alphabet N, November. Now, since this is a perpendicular, the angle which is made at November or N is a right angle. Now, if we measure Charlie to November distance, C to N, Charlie to November distance, as per our scale used, this will give us the range of the target at the CPA, at the closest point of approach. So this is the closest that our ship and the target would be at any point of time. So Charlie to November measured as per our scale gives us the nearest approach or the range of the target at CPA. Now moving further, we denote own ship's course and distance in the plot. The own ship course is plotted from point O. We draw our course from point O in the reverse direction. So whatever course our vessel is steering, the own ship is steering, is plotted from point O in the reverse direction. So let me show the own ship course. Starting from point O in the reverse direction, we draw this vector, the green color vector which you see on the screen. And this vector, end of this vector, the free end of this vector is named as W, that is whiskey, and whiskey to Oscar represents the own ship's course and distance in the plotting interval. The plotting interval is for 12 minutes, 0800 to 0812, and vector WO, whiskey Oscar, represents the own ship course and distance covered within this plotting interval. Now, important thing to remember is our course is plotted in the reverse direction from point Oscar. So it is plotted in the reverse direction. The actual course which the ship is steering is whiskey Oscar. Now, once this much of plotting is done, we can now easily obtain the target's course and distance during the plotting interval. How to obtain that? We will join point W with A, whiskey to alpha. Let us join whiskey to alpha line. You can see the maroon color vector coming up on the screen. This maroon color vector, whiskey alpha, represents the target's course and the distance covered by the target during the plotting interval, that is for 12 minutes, 0800 to 0812 hours. Now, whenever we do plotting, we also show the own ship course as a arrow on the circumference of the plotting sheet. You can see in this particular example, own ship is steering a course of 340. So we make a small arrow like the one which you see on the diagram on the plot, representing the course steered by own ship, and along with this course steered arrow, we also show the speed with which our ship is moving. So at present, our ship in this particular example is steering a course of 340 and is moving at a speed of 15 knots. This is also shown in the diagram, and you can see it is matching with Whiskey Oscar vector. Whiskey Oscar vector represents the course steered, which is 340, and the distance Whiskey to Oscar represents the distance covered by own ship in a period of 12 minutes, which is our plotting interval. So beta, any doubts coming in your mind up to here, please have a look and let me know.
Sir, where do we mark this distance from? Initially, like for 0800, bearing was given.
Right. So
And
how do you
distance,
find out the distance between Charlie and Oscar, correct?
Charlie and Oscar.
Is that your question, beta?
No, sir. Initially, you plotted this O.
Right.
Right. So we had the bearing and distance also, right?
Right.
No.
That will be given to us, the bearing and distance of the target at 2 times.
So, sir, distance where we'll plot from?
Okay. Let us say the target Oscar was at 10 miles at 0800.
Okay,
So we know
from
the bearing
our-
was 0 to 0. This 10
Understood.
miles is the distance between Charlie and Oscar. Charlie is own ship and
Yeah.
Oscar is the first observation. So Charlie to Oscar will be 10 miles. And since we have taken a scale of 1 centimeter is equal to 1 nautical mile, Charlie to Oscar will be 10 centimeter as per your scale.
Okay, sir.
Got it, beta?
Got it.
Okay. All the distances are measured from the center of the radar plotting sheet. The center of the radar plotting sheet marks your own ship's position.
Okay.
Okay, all right. So, chale beta, shall we move ahead? All okay?
Yes.
Okay, beta, great. Moving ahead.
Sir, just one more.
हाँ,
Sir,
बोलो बेटा.
so यहाँ पे it is 1 cm equal to 1 mile. So the 10 cm का आंक मारेंगे, right?
That is
From
correct,
C.
beta. Charlie to Oscar will be 10 centimeters.
Okay, sir.
Now let's move on to our next very important concept of aspect. Aspect is the relative bearing of own ship as viewed from the target. Or it can also be defined in a different way, that is, aspect is the angle between the target's course and the line of sight from the target to own ship. Let us try to understand it from the plot. Let us show the target ship at 0812 hours. On our plot, it will be at location A. We know the course of the target is WA, so target is moving in the direction of vector WA. Let us show the target at 812. You can see the target now on our plot. Let us extend the heading of the target. This blue color line represents the heading of the target vessel. Now let us plot the bearing of own ship from the target. So as viewed from the target, own ship's bearing is what we are going to plot. Own ship in our plotting is at the center of the plot, that is at point C. So from the target, I draw a line passing from point C, and it represents the relative bearing of own ship from the target. Now the angle between these two, that is the target's course and the bearing of own ship from the target, is known as the aspect. Let us show it in the diagram. This red color angle which you see in the diagram is the aspect. Now aspect is expressed in degrees from 0 degrees to 180 degrees, red or green. Red indicates that own ship is on target's port side. The situation which is happening right now in our plot, own ship is on the port side of the target. That's why the aspect is red. Green indicates that own ship is on the target's starboard side. So if own ship was on the target's starboard side, we will denote this aspect as green. Now aspect is a very important data point for collision avoidance because our rules of the road are dependent upon the aspect. Knowledge of the bearing of a target from own ship and knowledge of the aspects gives us an idea of the angle of approach between the two ships. Now this angle of approach is very important from the ROR point of view. Go ahead with your doubts now, beta.
So this aspect is at 0812.
That's correct, beta. It is at 0812.
Yes.
So any more doubts up to here, beta?
No, sir.
This aspect could be asked at 000 also?
Usually they require the aspect at the most recent time, but yes, they can ask you the aspect at 0800 also. They can ask you. So for that, you will have to measure the same angle at 0800. So, but it is very impractical. I don't foresee or remember a question in which the aspect is asked at a previous time. Usually it is asked for the latest time.
Oh. So one more doubt.
Bolo beta.
Sir, why the aspect is for the target, not for the us where is the vessel, because we are taking action, not target.
Okay, beta, basically you are trying to see how is your ship approaching the target. You see, when we talk of ROR, when you see a overtaking situation, now when you want to ascertain whether you are overtaking another vessel or not, you will have to see how many points above the beam your ship is with respect to the other ship. So that is why we measure this angle of aspect at the target vessel, so that we come to know how we are approaching with respect to the target's heading.
So
you're coming broken.
So sir, in the exam, aspect means for the target only.
Ask again, beta. Ask again.
So sir, in the exam, if they ask what is the aspect, that aspect is for the target only.
Aspect is always the relative bearing of own ship from the target. You assume that you are standing on the bridge of the target ship and you are taking bearing of own ship. That is what is aspect. Okay, so my voice was coming broken. Is it okay now, beta?
Yes, now it's okay.
Yes, sir, it is okay.
Okay, all right. So चलें बेटा आगे, comfortable?
Yes, sir.
Okay, all right. Now, having understood the basics of plotting and also the references which we use in our plot, we are now in a position to work out a practical question. So let us see our first example. You can see the question on the screen. Own ship is steering a course of 340 degrees true at a speed of 15 knots. Observes a target bearing 020 degrees true and at a range of 12 miles at 0800 hours. And the target ship is bearing 017 degrees true at a range of 9 nautical miles at 0812 hours. Find the CPA range, closest point of approach range, and TCPA. TCPA is the time for closest point of approach, course and speed of the target, and also the aspect of the target at 0812 hours. So we see in the question, two observations have been taken using the radar. First observation has given us the target bearing 020, range 12 miles, taken at 0800 hours. And the second observation taken at 0812 after a duration of 12 minutes. This 12 minutes is our plotting interval. The second bearing is 017 degrees true and the range of the target at 0812 is 9 miles. So let us now apply our knowledge and plot this target and find out the solution. Let's open up the plotting sheet. You can see the plotting sheet coming up on the screen. Now let's first of all mark the own ship's course and speed on the circumference. Our course is 340 degrees true. So we mark an arrow on the circumference in the direction of 340 and we also mention our speed alongside it, that is 15 knots. Let us now mark the center of the plot, center of the radar plotting sheet as C, Charlie. This is the reference we use for the center. And let us also mention the scale on our plot. The scale which we are going to use for this question is 1 centimeter equal to 1 nautical mile. Let us now plot the first bearing and range. The first bearing is given as 020. So from the center in the direction 020 at a range of 12 miles. 12 miles as per our scale means 12 centimeters. So in a bearing of 020 at a range of 12 miles, we mark our first position. This is the position of the target at 0800 hours and we know that this position is named as O. Now let's plot the second position of the target. Second observation is bearing 017. So in a direction of bearing 017 at a range of 9 nautical miles. So 9 nautical miles as per our scale is 9 centimeters from point C. We plot the second position of the target. Now this is the position of the target, relative position of the target at 0812 hours and it is named as A, alpha. So Oscar is our initial observation position. Alpha is our second observation relative position. Now we join O to A and we extend this line further. So joining O with A and extending further, this line gives us the line of approach, LOA. The line of approach is represented by a double arrow. So let us mark a double arrow here. Now from the center of the plot, that is point Charlie, we drop a perpendicular to the line of approach. This perpendicular, the position or the point at which it intersects the line of approach is named as N, November, and this November represents the CPA of the target, closest point of approach of the target. Now, since Charlie November Cn is perpendicular to the line of approach, the angle which is made at November will be a right angle. Now, if we measure this distance from C to N, Charlie to November, this distance gives us the CPA range. So in this case, we measure this distance Cn and it comes to 1.9 miles. So the CPA range of this target is 1.9 miles. The second thing which you observe is that the target is crossing from the bow of our own ship. Own ship is steering a course of 340 and this relative line of approach passes from the bow side of our ship or from ahead of our ship. Now to obtain the TCPA, we measure the distance from alpha to November, A to N. This distance is measured. Now we are aware that the target has relatively moved from Oscar to alpha in a interval of 12 minutes. So the distance Oscar to alpha is covered in a interval of 12 minutes. We have also obtained the distance alpha to November. So interpolating with the approach of the target, we find out how much time it would take for the target to reach at November. So we are aware that the distance OA is relatively covered by the target during the plotting interval of 12 minutes. Hence, we find how long it would take to cover the distance alpha to November by using simple interpolation. So using simple interpolation, alpha November divided by Oscar alpha multiplied by 12. This gives us a duration of 35 minutes. Distance Oscar alpha was covered in 12 minutes. Now from alpha to November, it will be covered in 35 minutes. Now once we have obtained this duration 35 minutes, we can add these 35 minutes to our second observation time, that is 0812 hours. So 0812 plus 35 gives us the time, exact time when the CPA would occur. So that comes out to be 0847 hours for this particular question. Any doubts coming up to here, beta?
Sir, in this CPA from 0812, we have taken up AN divided by OA into 12. Is this 12 equal to the interval, equal to this plotting interval?
Yeah, that's correct, beta. That is the plotting interval.
Okay, sir. Okay.
Basically, OA was covered in 12 minutes. Okay. 1 mile will be covered in 12 divided by OA, and alpha November will be covered 12 divided by OA multiplied by alpha November. So that's simple interpolation. Clear, beta? Any doubts coming up to here?
Yes, sir.
Go ahead, beta.
So, sir, you said that the target vessel will be crossing astern of the own vessel. So how we came to know
Ahead,
that,
beta. Ahead, not astern. It will be crossing ahead from our bow. That's because you see, beta, our ship is steering 340. So you can imagine at point Charlie, if you want, you can make a rough diagram of our ship. The heading will be in the direction of 340, in the direction of the green color arrow which we have made on the circumference. So you can clearly see that this ship is crossing from our bow side.
Okay, sir.
Okay, great. Any more doubts up to here, beta? Very good, beta. Great. Moving ahead. Let us now find out the course and speed of the target and also the aspect. Now we draw on-ship's course and distance from point O in the reverse direction. So from point O in the reverse direction, we draw our course and the distance covered by on-ship in 12 minutes. So the end of this vector is named as W whiskey. So you can see the whiskey Oscar vector, the green color vector coming up in our plot. Whiskey to Oscar vector represents on-ship's course and distance in a period of 12 minutes. Now, from point whiskey, we draw a line going up to point alpha. So we join whiskey to alpha. This whiskey to alpha vector represents the target's course and the distance covered by the target in the plotting interval, that is 12 minutes. So you can see the red color vector W to alpha. The direction of the arrow shows the course of the ship. So W to alpha, WA vector represents the target course and the distance covered by the target in the plotting interval, which is 12 minutes. So using our circumference as a compass rose, we now find out the direction of target whiskey alpha, WA, and it comes out to be 273 degrees. So the target's course is 273. We also measure the distance W to A, whiskey to alpha, using our scale, plotting scale, and this distance comes out to be 2.5 nautical miles. So the target has covered 2.5 miles in a interval of 12 minutes. Interpolating this value gives us the speed of the target as 12 knots. So we have obtained the course as well as the speed of the target ship. Now to find out the aspect, we first read off the bearing of our own ship, which is at point Charlie at the center of the plot, from the target ship Alpha. So again, using the plotting sheet, the graduations on the plotting sheet as a compass rose, we find out the direction Alpha to Charlie, bearing of Charlie, that is own ship, from the target, that is Alpha at 0812. And when we read this from the plotting sheet, this bearing comes out to be 197 degrees. We know the course of the target is 273. Let us show the course of the target, extend the course of the target. W2A was the course, this is extended, and the angle between these two lines, the red color angle which you see in the diagram, this is the angle between the target's course and the bearing of own ship from the target, is the aspect, and this aspect in this case is 273, which is the target's course, minus 197, which is the bearing of own ship from the target, and this gives us a value of 76 degrees. And since our ship is on the port side of the target, this is 76 degrees red. So we have obtained the aspect as 76 degrees red. The aspect is also shown in the plot for clarity, but once you have understood the concept, there is no need to show the aspect on the plot. It can be easily calculated in the working alongside the plot. So you can show it in the calculation. 273 minus 197 gives you 76 degrees red as the aspect. Now, one more important thing, we have obtained all the items which were required in this question, the CPA range, the TCPA, the course and speed of the target, and the aspect at 0812. One more thing which can be done from this plot is we can also predict the future positions of the target. We know the OA line extended is the relative line of approach. So if you want to predict the position of a target, the range and bearing of a target at any particular time, it can be done. So let us say if we want to find out the position of the target at 0820, the future position can be predicted. We know the target will be moving on line Oscar alpha, and we know the rate at which the target is moving. It is covering distance Oscar alpha in an interval of 12 minutes. So using this rate and this particular line, we can predict any future positions of the target. So that completes our basic plotting question. Two observations given to us: how to find out the CPA, the TCPA, course and speed of the target, and the aspect. Go ahead with your doubts, beta.
Sir, Vaibhav here.
Bolo beta.
Sir, this CA line has to be drawn on the plotting sheet or not in the examination?
You can draw it. You can draw it if it is not making your plot too much cluttered. Always better to draw.
And so one more question is alongside this plot, this calculation of aspect is just this subtracting the angle and from the course, or adding or subtracting the angle from the course is sufficient to show the calculation along with the plots.
Yeah, that's enough, beta. You don't need to explain why you are doing this. Okay. Just do the calculation and that should suffice.
Okay, sir. Thank you, sir.
Okay.
Sir, but if we don't join this C and A, how can we do it without drawing this line?
Yeah, that's right, beta. You will not be able to measure the angle. You can do it on answer sheet also. Even if you don't draw Charlie alpha or alpha Charlie, you can measure this alpha Charlie direction and write it down directly on your answer sheet. That also can be done.
Okay.
Sir, Maggie here. So this 1.9 which you got, that one I was getting as 2.1. So is it okay like this? Something?
Perfectly all right, beta. You see, whenever you do any plotting, whether it is chart work in navigation or it is radar plotting, there are always going to be plotting errors. All the tools which you are using, your parallel ruler or set square, sliding ruler, compass, divider, even the scale, protractor, 3D, all these things, they are going to have their own errors. So a little bit of difference in the answers is perfectly all right. What is important is that the fundamental should be correct and answers can vary a little bit. Now there is no limit or range how much a answer can vary because it all depends upon the scale which you have taken. If the scale becomes bigger, the error will also become bigger. So it's perfectly all right.
Thank you, sir.
Clear, beta? Okay. Okay, great. So chale beta आगे. Okay, just a minute. Let me. अच्छा बेटा मुझे ये बताओ कि अप टू हियर ओके, ओवरलोड तो नहीं हो रहा? सब याद आ रहा है जो पहले किया हुआ है?
Yes, sir.
Okay, all right बेटा, great. Okay, अब बेटा एक और छोटा सा कॉन्सेप्ट है जो इन बेसिक प्रॉब्लम्स के साथ आता है. That is the concept of finding out the set and drift. Okay, what they do is in these questions, they sometimes give you a fixed object. कोई लाइट हाउस दे देंगे या एंकर्ड शिप बोल देंगे या रेकन, बीकन, एनीथिंग और ए पॉइंट ऑफ लैंड, उसके आपको ऑब्जर्वेशन दे देंगे, रेंज एंड बियरिंग, and then they tell you to calculate the set and drift present or prevalent in that area. So वो एक और छोटा सा concept है. So are you comfortable? Can we continue with that concept? Okay. Okay, beta.
So voice was broken last.
Yes.
Okay. Anybody else also feeling broken voice?
सर बीच बीच में होती है कभी.
Okay, all right. Because from my side, the net is showing perfectly all right.
अभी okay sir.
Okay. Okay, all right. In case you miss something, just ask me once I pause the slide. I'll repeat that once again, beta.
Okay.
Okay, so we are moving on to the concept of how to find the set and drift of the current if a fixed object is given to us. Let's go. Now moving further, using our knowledge and technique of radar plotting, we can also obtain the set and drift of the current which is affecting our ship in a particular area. In some of the radar plotting questions, this concept may be required. So let us now see how do we use the radar plotting technique to obtain the set and drift of the current. So let's open up our radar plotting sheet. Let's mark the center as C Charlie. Let us show the scale which we are going to use. The scale is 1 centimeter is equal to 1 nautical mile. Let us now show the own ship's course and speed. Our ship is steering the same course 340 with a speed of 15 knots. Now to obtain the set and drift of the current, we need to have a stationary target available to us for observation. The stationary target could be a lighthouse, a buoy, wrecken, beacon, point of land, anchored ship, anything which is given as stationary in the question. So let's assume that we have a lighthouse inside and we have observed that lighthouse using our radar and we have obtained a range and bearing. So let us now plot the range and bearing of that lighthouse on our plot. Let's assume that the lighthouse was observed at this particular bearing and at this particular range. So we have plotted it using the range and bearing on our radar plotting sheet. Let's assume that this observation was taken at 0800 hours. And as per our naming, we name this lighthouse position as O Oscar. Now, after a certain time, after our plotting interval, the lighthouse was again observed. And this time the lighthouse is at this relative position. This is the bearing of the lighthouse and Charlie to lighthouse represents the range. This observation is taken at 0812 hours and as per our naming, we name it as A alpha. Now, if we join the line Oscar to alpha and extend it further, this will give us the relative line of approach represented by 2 arrows. So you can see the relative line of approach. Now, in the next step, we mark our own ship's course and distance. So from point O in the reverse direction, we mark out this vector. You can see the green color vector. The length of this vector is equal to the distance covered by own ship in the plotting interval. The free end is named as W Whiskey, and you can now see Whiskey to Oscar represents the course and distance of the ship within the plotting interval. Now we also join W to A, exactly the same method which we did when we were plotting a target. So we join W to A, Whiskey to Alpha. You can see the red color vector joining Whiskey to Alpha. Now this red color vector gives us the set and drift of the current. Alpha to W, pay your attention now. Alpha to W gives us the set and the drift of the current during the plotting interval. One very important thing to understand here is when we were plotting a target, the target's course was whiskey to alpha. But when you are obtaining the set of the set of the current is in the direction alpha to whiskey, not whiskey to alpha. It is from alpha to whiskey. A to W gives us the set of the current. Now, why is that the set of the current is in the opposite direction? It can be easily understood. Let's assume that if there was no current in the area, our ship was proceeding on a course of 340. So the lighthouse would move relatively in exactly opposite direction. So from O, the lighthouse would be moving on this green color track. And after 12 minutes, the lighthouse will be at the location of whiskey. But instead of falling at whiskey, the lighthouse has instead gone to the location alpha. Now the lighthouse is stationary, lighthouse does not move. So how has it gone from whiskey to alpha? Actually, what has happened is the lighthouse has not moved, but there is a current affecting our ship, and our ship has moved in the opposite direction. Our ship was no more at Charlie. Our ship has traveled in this direction because of the current, and relatively the lighthouse appears to go from point whiskey to alpha. Therefore, the set of the current is
Sir,
from
sorry to
alpha
interrupt, but
to
we are not able to
whiskey,
see the slides.
shown by the direction of the arrow. And if you measure the distance between alpha to whiskey, this gives you the drift of the current.
Excuse me, sir.
This is. Go ahead, beta. Who is not able to see the
Sir,
slide?
yeah, I am Pradeep, sir. I am not able to see the slides from last 5 minutes.
Okay, all right. Beta, what about other people? Can you see the slide?
Yes, sir.
Okay. So Pradeep, you just need to log out once and log in again, beta. Just disconnect from the meeting and join again. The slide would appear. There is some net connectivity issue on your end. Okay, beta, got it? Yeah, Pradeep, got it, beta? Are you doing that?
Yes, sir. Yes, sir. Thank you. Now I can see.
Okay, all right, beta. So if this happens to other people also, if you are not able to see the slide or the screen has frozen, you just disconnect and join again. Immediately you will be able to see the slide. This happens because there is a fluctuation in the internet speed on your side. Okay, all right. The drift of the current within the plotting interval. In our example, the plotting interval is 12 minutes. So by interpolating, you can find out the rate of the current also. The rate will be the drift in 1 hour. So this completes the technique of obtaining the set and drift of the current using a stationary object. So beta, have a good look here and let me know any doubts coming in.
सर एक बार करंट का प्लीज एक्सप्लेन कर दीजिए वापस से.
What is the specific doubt in current, beta?
Sir, regarding direction, sir.
Okay, you mean to say why it is alpha to whiskey, why not whiskey to alpha?
Yes, sir.
Okay, all right. Now look carefully, beta. If there was no current in the area, our ship was moving in the direction from whiskey to Oscar. So lighthouse being stationary would relatively move exactly in the opposite direction. So we would expect to find the lighthouse at whiskey after 12 minutes, correct?
Yes, sir.
Now the lighthouse is not at whiskey, the lighthouse is at alpha. Now if this was a object which was moving, we could have understood that it has moved from whiskey to alpha, it has its own engine and it has moved. But this is a fixed object, so that tells us this cannot move. So how has it relatively gone from whiskey to alpha? Actually, the object has not moved. What have happened is our ship has moved in a direction alpha to whiskey because of the current in the area. Now, when our ship moves in the direction from alpha to whiskey, the fixed target appears to move in the relatively opposite direction. So that is why alpha to whiskey is the current which is affecting our ship. It is pushing our ship in the direction from alpha to whiskey, and relatively the lighthouse gets in a position from whiskey to alpha. Getting clear, beta?
Yes, thank you.
Sir,
Okay.
I have a doubt.
Bolo, beta.
Sir, we are considering that lighthouse is a fixed object. So
Right.
from here it is 0800, like that is the fixed object, and 0812 how we are considering like another position.
No, I didn't get your doubt, beta. Can you speak
Sir,
again?
my
Ask
doubt
again.
was like my doubt is lighthouse is a fixed object.
Right.
So it was 0800. It was at position O.
Right.
And then at 0812, we are considering that lighthouse has moved from O position to A position.
That is correct.
So, sir, it is like we are considering the fixed object to the lighthouse. So, how why we are moving the lighthouse like that?
Okay. All right. All right. I got your point, beta. Object fix है तो वो move क्यों कर रहा है? It should remain at Oscar only. Correct?
Yes, sir. Yes, sir.
Now, beta, this is a relative radar picture, beta. अगर आप किसी श्योर ऑब्जेक्ट की तरफ जाओगे तो आप उसे ट्रू प्लॉट में नहीं जा रहे हो. आप यू आर नॉट डूइंग ट्रू प्लॉटिंग. इट इज ऑन ए रिलेटिव मोड, नॉट ट्रू मोड. आपका शिप स्क्रीन पे मूव नहीं कर रहा है. योर शिप इज गोइंग टू रिमेन एट द सेंटर ओनली. द टारगेट इज गोइंग टू मूव. अगर आप कोस्ट लाइन की तरफ जा रहे हो तो आपका शिप कोस्ट लाइन की तरफ नहीं जाएगा, कोस्ट लाइन आपकी तरफ आएगी. आर यू गेटिंग दिस बेटा?
Yes, sir.
Did
Got
that
it, sir.
got it? Okay, all right. So Oscar to alpha is not the actual movement of the lighthouse, it is the relative movement of the lighthouse. Actually, our ship is moving in a direction from alpha to Oscar. That is our course made good. Okay, great.
Sir, one
So,
question.
bolo beta.
Sir, can you repeat how we will calculate set and drift?
Okay. बेटा सेट के लिए तो you align your parallel ruler to alpha whiskey and then you shift it to the center. So wherever that sliding roller takes you to the circumference, that immediately gives you the set or the direction of the current. Right, beta? Got it?
Okay.
Okay. Now about the rate of the current, you see alpha to whiskey is the drift in 12 minutes. Now rate is for 1 hour. So you have to interpolate whatever a value, alpha whiskey value you get from the plot using your scale, that is for 12 minutes. Interpolate it for 60 minutes. Or in other words, it is very simple. Multiply this by 5. It will give you the rate of the current.
Okay.
Got it, beta? Clear?
Yes, sir.
Okay, all right. Any more doubts?
Sir, one small doubt. The set and drift can only be ascertained if we have a fixed object, right? So if in question
That's
there is no
correct.
fixed object, that means set and drift won't be asked in that question.
No, beta. Wherever set and drift is asked, they have to give you a fixed object.
Okay, sir. Thank you, sir.
Okay. Great. So if you are comfortable, shall I close this out now, beta?
Yes, sir.
Okay, great. So that basically covers up our first topic, the basic radar plot for today. Now I will not do any more radar plotting. So let me close this presentation. Okay, all right. So, up beta, before we proceed ahead, is it comfortable to move or you want to have a short break?
Break, sir.
Move,
No,
sir. Move.
comfortable to move, sir.
Move, sir.
Comfortable
Move.
to move, sir.
Sir,
Oh,
we can, it's up to you, sir. We can move.
Short break.
okay. No problem. Take a 5 minutes break, beta. Take a 5 minutes break. Get back after 5 minutes. Okay?
Okay, sir.
Okay.
Okay, sir.
Thank you.
Okay, beta, sorry I got a bit delayed, got a important call. So anyway, so everybody is back. Shall we restart?
Yes, sir.
Okay, all right. So बेटा रडार प्लॉटिंग तो मैं यहाँ पे ही रोक रहा हूँ. This is a basic radar plot so that you can practice these basic radar plot questions. अगर आप शिपबोर्न रडार बुक देखेंगे तो उसमें जो पहला प्लॉटिंग का चैप्टर है that is on a basic radar plot. उसमें कुछ एक सॉल्व्ड एग्जांपल दी हुई हैं. So practice those solved example. You don't need to do all the examples. Just do that much with which you are comfortable and confident that you are able to solve these questions. And as I told you, a little bit of difference in the answers is not to be bothered. A difference in the answer, slight difference in the answer is perfectly all right. That happens because of plotting errors. So अब बेटा I am picking up a simple equipment because आज के लिए आपका homework ready हो गया है. So I'm picking up a simple equipment so that you can just listen to it as a story and we can cover that up. So I'm picking up Eco Sounder for today. Okay, beta?
Sir, this floating for practice, shipboard alpha by Captain Subramaniam book you talking about.
That's right, beta.
Okay, so we need to practice with that. Sir.
Yeah.
Sir, what will be the chapter number?
बेटा just have a look, open the book. Radar plotting का जो पहला chapter है ना, first chapter, that gives you the basic radar plot. Just do that.
Okay.
Okay. Initially, that books give you the theory of the radar. So just skip the theory portion. Go to radar plotting directly. The first chapter gives you a basic radar plot.
All right.
Okay.
So can you please repeat the last one because I didn't get your voice.
No, beta, I simply told that you need to practice these basic radar plotting questions to be ready for advanced problems tomorrow.
Okay, sir, Gopal, thank you.
Okay. And for now, I'm picking up a simple equipment which you can listen to as a story and you can relax. So I'm picking up Eco Sounder for that. So if all of you are comfortable, we can start off with the Eco Sounder presentation.
Yes, sir, we can.
Okay, all right. Just give me a minute, I'll put up the Eco Sounder presentation.
Sir, regarding this presentation, it will be sent to us in PDF, sir?
No, beta, as I told you, I'll be sending you PDF notes. So for Eco Sounder also, मैं आपको PDF notes भेज दूंगा. So you don't need to write anything.
Yes.
Okay. Just refer to the basic book. So reference book plus my notes should suffice.
Yes, sir.
Okay, all right. So let's go into the Eco Sounder. In this presentation, we are going to learn about Eco Sounder, which is a device used for sounding the sea or getting to know the depth of the sea using the echoes or acoustic waves. Eco Sounder is an electronic device that uses the acoustic wave echoes to find the sounding or the depth of water. That is why the name Eco Sounder. Acoustic waves are basically a series of compression and decompression, also known as rarefactions, propagating through a medium. In our case, the medium is the seawater. These waves travel at the speed of sound and hence are called as acoustic waves Acoustic basically means related to sound. Moving ahead now. Let us first go into the principle on which the echo sounder works. Now, in an echo sounder, short pulses of acoustic waves are transmitted downwards from the transducer towards the seabed. In the diagram, you can see a particular ship here. We have the transducer fitted at the keel. You can see these acoustic waves are transmitted downwards toward the seabed. They get reflected from the seabed and are received back by the transducer. So these acoustic waves, they get reflected back from the seabed. The reflected waves are received back by the transducer, and the time taken from the transmission to the reception is measured. Now we are aware that the speed of sound through the water is 1500 meters per second, and using this speed as well as the time taken by the echo to come back, we can calculate the distance traveled by the waves. We have the time which is taken by the wave to go down up to the seabed, reflect and come back to the transducer. We know the speed of the acoustic wave, 1500 meters per second. So the distance traveled by the wave is given as speed into time. So speed multiplied by time gives us the distance traveled or covered by the wave, and you can see the distance covered by the wave is twice the depth of water, 2 times the depth of water. So this distance divided by 2 gives us the depth of the water. Clear up to here, beta? Okay, great. Moving ahead. Let us now have a look into the various components within the echo sounder system. The first component which we have is the pulse generator. You can see that in the diagram. The pulse generator basically produces electrical signals or electrical oscillations which are sent to the transmitter. The transmitter is included in the transducer part of the echo sounder. The transducer includes the transmitter as well as the receiver. Now, once the transmitter receives the electrical oscillations, it converts these electrical oscillations into acoustic wave signals. So this is fitted at the keel of the ship. As soon as it receives electrical signal from the pulse generator, it transmits acoustic waves towards the seabed. These acoustic waves go towards the seabed, hit the ocean floor, return back, and when they return back, they are received by the receiver. Receiver is also included in the transducer itself. The receiver receives these acoustic signals, acoustic echoes, and converts them into electrical oscillations or electrical signals. Now, these electrical signals, which are received by the receiver, are very, very weak, because these acoustic wave echoes, they suffer substantial loss of energy when they are traveling through the seabed, undergo reflection at the ocean floor. So the receiver signals are very, very weak. These signals are then converted into electrical oscillations or electrical signals and sent to the amplifier. The amplifier amplifies or strengthens these weak electrical signals, and these strengthened or amplified signals are then sent to the recorder. We have the recorder which receives these amplified signals and makes a mark on the recorder paper. If it is a digital kind of echo sounder, we see the markings on the digital screen and the cycle is completed. So these are the different parts involved in a echo sounder system. Moving ahead now, beta. Let us now try to understand the working inside a recorder. Now within a recorder unit, a stylus is mounted on a continuous circular belt. So if you have a look at the diagram, you can see this is the belt on which the stylus is fitted. So this is the belt and you can see the stylus. This arrow shows the stylus. This is the recording paper. You can follow the laser pointer. This is the recording paper. This is the stylus and this is the belt which we are talking about. Now this belt is driven at a constant speed by a stylus motor. There is a motor fitted and that motor drives this belt with a constant speed. Also, if you look here, there is a magnet which is fitted on the belt. This magnet triggers the transmitter to transmit a pulse at every rotation of the belt. You see when the belt is rotating and when the stylus reaches the zero mark is somewhere here. When the stylus reaches the zero mark, this magnet sends a signal to this particular sensor. The sensor catches this magnet and this sensor then sends a signal to the transmitter which is there in the transducer and it transmits the echo towards the ocean floor, towards the seabed. So same thing is mentioned here. A magnet which is fixed on the belt triggers the transmitter to transmit a pulse at every rotation of the belt when the stylus is at the zero mark on the paper scale. So the pulse energy is beamed towards the seabed and along with this, some of the energy leaks back to the receiver. As soon as the transmission is made, some energy leaks back to the receiver and this leaked energy is sent back towards the stylus and it makes a mark on the paper which is called the zero mark or the zero line or transmission line. So we see a small mark as soon as the transmission is done, indicating the zero line on the recording paper. Now this echo which is transmitted by the transducer goes to the ocean floor, is reflected back, received by the receiver after covering the distance equal to twice the depth. Again, the transducer receives this energy and sends back a signal to the stylus and the stylus marks that depth on the paper. By the time the echo has gone down to the ocean floor and come back, the stylus has also traveled from the zero mark and it reaches at this particular point. The speed of the stylus is basically half of the speed of the acoustic echoes. That means if the acoustic echoes cover 1500 meters per second, the stylus covers a distance of half of that amount, 750 meters, on this particular scale on the recording paper. So making a mark on the paper at the required depth. Clear up to here, beta? Okay, great. Moving ahead. So the same thing is mentioned here. During the time taken for the echo to return from the seabed, the stylus has moved down from the zero mark and hence makes a mark on the paper at a distance appropriate to the depth. The echo has gone down to the seabed and has come back. During this time, the stylus has moved from the zero position and reaches up to a particular depth here, and that depth is marked on the paper. A marked scale is provided on the side of the recording paper. You usually have the depth indication in meters, fathoms or feet to read the depth. This cycle is repeated for every rotation of the stylus and also the recorder paper is pulled across the display and a profile of the seabed is obtained. So this recording paper also has a small motor because of which it is traveling in the horizontal direction, and that creates a profile of the seabed on the recording paper. Now it is very important for the working of the echo sounder that the speed of the stylus must remain constant to ensure correct depths being recorded by the echo sounder. Moving ahead now. Let us now have a look at some of the technical parameters which are present in an echo sounder. The first parameter is the pulse length. Pulse length is basically the duration between the leading edge of the echo and the trailing edge of the echo. It basically tells us what is the length of the pulse of the echo, or the length of the echo which has been transmitted. The pulse length determines the minimum distance that can be measured by the echo sounder. The minimum measurable distance is equal to half of the pulse length. If the pulse length is 2 meters, the minimum distance which the echo sounder can measure is 1 meter. Now for shallow waters, short pulses are used, whereas for deep waters, long pulses are used. In shallow waters, we have very less depth of the water, so that's why a short pulse is required, because the pulse length determines the minimum distance which the echo sounder can measure. And in deep waters, we use a longer pulse length, because in deeper waters, a short pulse length may lose substantial amount of energy, and its reflected echo may be very, very weak to catch up. The second technical parameter which we have is the pulse repetition frequency, in short known as PRF. It is basically the number of pulses transmitted by the echo sounder per second. The pulse repetition frequency determines the maximum range that can be measured. Both these settings, the pulse length as well as the pulse repetition frequency, are automatically selected, and they change as the range scale is changed by the user. We do not usually, in most of the equipment, we do not need to make any changes in the pulse length and pulse repetition frequency manually. As soon as we change the range of the echo sounder, both these parameters are automatically set to the optimum values. For lower ranges or lower depths, a high PRF is used, whereas for higher ranges, a low PRF is used. Now, when the depth of water is more or the range is higher, we need to have substantial time between two pulses, because the echo is going to take longer time to hit the seabed and come back. So we need to have that time duration between two pulses, which leads to reduction in the pulse repetition frequency. So whenever the range is high, low PRF is used. For shorter ranges, high PRF can be used. Moving ahead now.
Sir, I have a doubt over here.
Yeah, go ahead, beta.
Sir, what will happen if we use only long pulses for shallow waters, as the minimum distance, measurable distance is half the pulse length, correct?
Right.
So it's better to use long pulses, no? What disadvantage would it make in shallow waters?
Okay, just a minute. Let me have a word with you face to face. Now, if you are in shallow waters and you use a long pulse, now you see, beta, it's like VHF transmission. Till the time the echo sounder is transmitting, if it is a long pulse, it will be transmitting for a long time.
Okay.
So till the time it is transmitting, it cannot receive back any echo. So you see, if the depth is very less, the echo is going to come back very quickly. And if it
Yes.
is still transmitting, it will miss that echo. It will not be able to measure the depth of water. That is why in shallow waters, we always use a short pulse so that the transmission ends quickly and the echo
Mhm.
sounder reception is on and it can receive the echo.
Okay. Yes. Sir,
Okay.
so in case of measuring deeper waters, when the wavelength is more, at that time, does the stylus speed also reduce? Because
Uh,
the time taken is more.
the stylus speed will reduce when you change the range of the echo
Range.
sounder.
Yes.
Okay. Not with the pulse length. The pulse length will automatically keep on changing. When you increase the range, let us say that you make the range double. When you make the range double, the same height of the paper now shows double the distance. So the speed
Yes.
of the stylus automatically becomes half.
Ah, understood.
Okay.
Yeah.
So
Okay.
one more
Let's
thing,
go ahead, beta.
Akib here, sir. So for lower depth, it is written higher pulse, higher RPF will be used,
Right.
and for higher depth, lower. This part, can you just explain, sir?
Okay, beta. Now it says is that for lower range we use a high PRF. High PRF basically means that lot of pulses are being transmitted in 1 minute. Okay. If you are transmitting a lot of pulses, high frequency means the transmissions are occurring very fast. Low frequency means the transmissions are occurring slowly.
Yes, sir.
Now, when the PRF is fast, that means the transmissions are going very fast. The gap between two transmission is very less.
Yes, sir.
Okay. It works for shallow waters, but when you go in deeper waters, you see the echo is going to take a longer time to go back and come.
Yes, sir.
Okay. Now, till the time the echo comes back, since the echo is taking long time, till the time the echo comes back, the transducer cannot start next transmission, because if it starts next transmission, it will not be able to catch that pulse. So it
Understood, sir.
needs to wait for that pulse to come back, and for that, the pulse repetition frequency has to be slowed down. Lesser number of
Lower.
pulses in a second.
Clear, sir.
Okay.
Yes.
Great, beta. So let's go back to the presentation. Okay, all right. Let's now go into the transducers. Let's now go into the transducer, have a look at what type of transducers are available. A transducer is a device that converts one form of energy to another. For example, in our case, electrical energy to acoustic waves and vice versa. In most of the cases, a single transducer acts as both the transmitter and the receiver. That means it is able to convert electrical energy to acoustic wave and also a acoustic wave to electrical energy. As we have seen earlier, this is located at the keel of the ship. Radio frequency energy when applied to a transducer or electrical signals when applied to a transducer will cause the unit to oscillate, and these oscillations will cause acoustic waves to be generated and transmitted in the water towards the seabed. These waves reflected back from the seabed, the echoes which are reflected back from the seabed, come back to the transducer, hit the transducer and generate oscillations. This causes a minute electromotive force, EMF, to be generated, which is then processed by the receiver and amplified by the amplifier to produce the necessary data for display. We have two types of transducers which are used most frequently in a echo sounder. These are number one, piezoelectric or electrostrictive transducers, and number two, magnetostrictive transducers, both working on different concepts. Let us see these two different type of transducers working now one by one. Moving ahead now. First, we go into a piezoelectric or electrostrictive transducers. You can see the diagram of a piezoelectric transducer. Piezoelectric or electrostrictive transducers use crystals like quartz or Rochelle salt. You can see this quartz or Rochelle salt piezoelectric element here in the diagram. It is fitted in the middle of the two yellow portions. If an alternating voltage is applied to the opposite faces of a flat piece of these piezoelectric materials, the crystal is going to expand and contract and hence vibrate, creating sound waves for as long as the vibrations continue. So you can see there is an electrode which gives a EMF or voltage to this piezoelectric element, and as a alternating voltage is applied to this piezoelectric element, this starts to vibrate, and these vibrations are passed on to the transducer surface and acoustic waves are generated. Now this process is reversible. That is, when varying pressure from a returning echo is applied to the opposite faces of the piezoelectric element, an alternating voltage is generated across the faces, and the same can be further amplified and used to activate an indicator. So initially we provided some alternating current voltage to the piezoelectric element. This started vibrating, and these vibrations generated the acoustic waves. As soon as these waves come back after reflection from the seabed, they hit the transducer again. That generates a vibration or oscillation in the piezoelectric element. And because of this vibration of the piezoelectric element, it generates a EMF, electromotive force or voltage, and this is passed on to the amplifier. Generally, in case of piezoelectric transducer, only one transducer is used for transmission as well as reception of the signals. And this transducer is always mounted at the keel of the ship in a pierced hull installation. That means we have to cut the hull of the ship as per the size of the transducer, and we have to fit that transducer in that particular cutting. Moving ahead now. Now moving on to a magnetostrictive transducer. In magnetostrictive transducers, a ferromagnetic material such as iron, cobalt or nickel is used, and a coil is wound around it. You can see in the diagram, this vertical line, this is the material which is a ferromagnetic material, and you can see there is a coil which is wound around it, which acts as a solenoid. Now this kind of transducers uses the magnetostriction effect, which is a phenomena whereby magnetization of the ferromagnetic material produces a small change in their dimensions. So what happens in this kind of a transducer is a voltage is applied to this solenoid coil, and as soon as the voltage is applied, a magnetic field is generated. You can see these yellow lines indicating the presence of a magnetic field. Now, in the presence of this magnetic field, the ferromagnetic material, iron, cobalt or nickel, undergoes magnetostriction. That means it reduces in size slightly and then increases in size slightly. This reduction and increase in the size of the material generates the oscillations, and these oscillations are passed to the towards the seabed, and that is how the acoustic waves are generated. Now, as these echoes go hit the seabed and come back, when they come back and hit the transducer again, it generates a vibrations. And because of these vibrations, there is a compression and expansion of the ferromagnetic material. Now, this compression and expansion of the ferromagnetic material generates a voltage in the solenoid coil. So this voltage is picked up by the receiver, sent to the amplifier, and it gives us the required return echo indicating the depth. So same thing is mentioned here. If a nickel bar is placed in a coil with an alternating current flowing through it called as a solenoid, the varying current and the magnetic field will cause the ends of the bar to vibrate and hence create a sound wave. Moving ahead now, beta. Now these vibrations, magnetostrictive transducer vibrations or acoustic waves, can be transmitted to the seabed through the ship's hull plate. You see, in a piezoelectric transducer, we saw that we have to pierce the hull, we have to cut the hull and fit the transducer. But the magnetostrictive transducer waves or oscillations are so powerful that it can be transmitted through the ship's hull plate. So this gives us an advantage. This allows us to fit the magnetostrictive transducer as an internal hull installation. We can avoid the piercing of the hull. It need not penetrate or cut or pierce the hull plate. It can be fitted as an internal installation, thus maintaining the required strength in the ship structure. So that's the advantage of the magnetostrictive transducers. We do not need to cut the hull plate to fit the transducers. In these kind of transducers, we need to use two transducers. One is used for transmission and the other for reception. You can see the diagram of a magnetostrictive kind of transducer. It is fitted as an internal hull installation. You can see the keel plate. You can follow the laser pointer. So this is the keel plate, and the keel plate need not be cut or pierced to install the transducer. The transducers can be fitted inside, but we need to fit two of them. One is required for transmission and the second one is required for reception. Same transducer cannot be used for transmission and reception again. Reason being that when a transmission is made, the hull plate starts to vibrate. And by the time echoes come back, this hull plate is still vibrating. So there is a mismatch. Both the echoes, they combine with each other, giving us a confusing signal. So we need to have a separate transducer fitted for the separate receiver fitted for reception of the echoes. Usually these are fitted toward the ship side, one fitted towards the starboard side of the ship and another one towards the port side of the ship. Moving ahead now.
Sir, one quick question.
Yeah, go ahead.
Sir, in piezoelectric transducers, you said also we will have a transmitter and a receiver separated, correct?
Right. No, in piezoelectric, it is the same beta. The same transducer is used as a transmitter as well as a receptor.
But sir, in your slide somewhere it was mentioned that it will be separate.
That is for magnetostrictive. Let's go back to the slides. Let's see. Okay, this is the piezoelectric one. You can see the bottom point. Generally, one transducer is used for transmission and reception of the signals.
Slides
we cannot
is not visible.
Oh, just a minute. Just a minute. Just a minute. Okay. So this is the piezoelectric one, beta. This is what we just now saw, magnetostrictive. I'm going back to piezoelectric now. This is piezoelectric or electrostrictive transducers.
So can we go to the next slide after this?
Okay, next one after this, huh? Okay, this is the one, beta.
Okay, this is so we had only one for that. Okay, maybe I read it wrong.
We had only one for piezoelectric or electrostrictive. you can see this bottom point states one transducer is used for transmission as well as reception.
Okay, sir, clear. So we will be getting
Okay.
these notes, correct? I mean the same thing in the notes.
I'll send you the notes in exactly the same format which I'm explaining you. So I'll
Okay,
send
sir.
you the notes.
Okay, sir, thank you.
Okay, all right. Now, you may get a question on explain the types of transducers which are used in the echo sounder. So these are the two transducers which you need to explain. And sometimes you may get a question on what are the difference between electrostrictive and magnetostrictive transducers. So let us go into the differences now.
Sir, no voice is coming.
Just a no words.
So as we discussed, we can now compare these two type of transducers, the pierced hull electrostrictive and the internal hull magnetostrictive. The integrity of the hull is compromised in case of a pierced hull transducer, and in a magnetostrictive transducer, integrity of the hull is maintained. The electrostrictive transducers can be serviced only during docking. There could be a gate valve type of arrangement fitted in some of the ships, which can allow servicing even when the ship is in water. In case of a magnetostrictive transducers, they can be easily serviced at any time whenever it is required because it is an internal hull installation and the transducer can be removed and fitted back without any issues. The electrostrictive transducers can operate, one transducer can operate as both transmitter and receiver. The magnetostrictive transducers requires dual transducers, one for transmission, other for reception. In a electrostrictive transducers, there are no hull losses. And in a magnetostrictive transducer, since the signals are passing through the hull plate, there is up to about 85% loss in power due to the hull plate coming in line of the signals. Dual transducers means twice the hull loss, means we require much more power in case of a magnetostrictive transducer as compared to electrostrictive. Electrostrictive type is generally cheaper and much lighter. The magnetostrictive one tend to be large, clumsy unit, heavy units, and they are used generally only on large vessels. Electrostrictive transducers are suitable for use at high frequency. Magnetostrictive are not suitable for use at high frequency as there will be a lot of magnetic losses. Some of the energy is reflected back by the hull plate. Clear, beta? Any doubts up to here?
Yes, sir. Just wanted to know, sir, in magnetostrictive type, won't the vibrations in the hull due to propeller and the waves create any interference in the
They will,
sensing
beta. They will. Because the magnetostrictive, the vibrations are coming through the hull plate. So any sources of noise, it could be the propeller or the engine room, pump room, sea chest also water will be going and coming out. So that is why their location has to be in such a way that they are far away from sources of any kind of noise. They have to be far away from the engine room, far away from the propeller. If there are bow thruster, it has to be at a suitable distance from the bow thruster. They cannot even be fitted close to the bow because the bow also will be pounding in heavy weather. That will also affect its accuracy. So you need to station it in such a way that the sources of noise are minimized.
Okay, sir, understood. And sir, in case of a piezoelectric transducer,
Right.
electrostatic, uh, the hull integrity is compromised. So are those used? Because that is dangerous in case of.
Mostly they are used, beta. 90% of the ships you will find piezoelectric transducers. Even though you have to cut the hull plate, their size is much, much smaller. So the opening which is made is much, much smaller. And what is done is they do some extra strengthening around that opening. Okay. And also what they do is they make a watertight sea chest, a small compartment where that is fitted. So even if there is a breach, if it gets broken, the vessel touches bottom, that's a sensitive area. Even if it gets broken, a limited portion will get flooded. So that is how the protection measures are taken.
Okay, sir. Thank you, sir. Understood. Thanks.
Okay. Great.
So which one is common or preferred on vessel?
The piezoelectric one is most common, beta. Most of the ships you will find a piezoelectric or electrostrictive transducers. They are much, much cheaper, easier to make. The sizes are much smaller and their accuracy is slightly better as compared to magnetostrictive. Magnetostrictive is heavy duty. So it's a big unit, a heavy duty unit. You can imagine when you have to pass the echoes from the hull plate, 15-20 millimeter thick hull plate, the echoes have to be very, very strong. So the power consumption is more, the vibrations are generated, the transducers are much, much more powerful. So they are rough and tough units. Okay.
Yes.
So most of the ship owners, they go in for piezoelectric units.
Thank you, sir.
Okay.
Sir, one small question.
Bolo beta.
Sir, this it doesn't matter whether we have a magnetostrictive or piezoelectric because but both have to be stationed in such a way that the noises are least in that area because both are working on the sound
Yes.
Frequencies itself,
Exactly.
right? So
Exactly.
both of them cannot be fitted extremely aft near the propeller or neither extremely forward near the bow. It has to be somewhere in between.
That is correct, beta. But piezoelectric can offset this effect, offset this error to a certain amount. It is more robust that way. The magnetostrictive is delicate. Magnetostrictive तो कहीं भी vibrations अगर होंगी तो उसका operation affect हो जाएगा. Piezoelectric one can go closer as compared to the magnetostrictive. So piezoelectric तो आप देखोगे कि sometime you may have it just front of the engine room or front of the pump room also.
Yes, sir. Yes, sir. Thank you, sir.
Okay. Great. So we have done the comparison. Now, beta, the next thing which is there is ranging and phasing. You get a question on ranging and phasing also. So two things we are left with. One is ranging and phasing and another is the errors of the echo sounder. So let's stop it here for today and we will continue this in the next session. So I'm stopping it here for today.
Excuse me, sir. I have one question.
Go ahead,
Sir,
beta.
what about the performance standard about this